Okay. Welcome, Laurette. Thank you.
Okay. Well, thank you. Thank you for having me. So here's a picture. And can you see me as well?
Yes.
Okay. Yeah, let me put on my, oh no, let's see.
You look
Right.
like Saint Laurette because you have your light above your head. So
Yes, I'm Saint Laurette.
always in place.
Yes. Okay. But I do want to do something with my hands. So that's why I wanted to make sure you could see me.
Not
what
well
you
known
see-
you're a saint. But yeah.
Okay. What you see here in 2D is halfway between two plates that are moving in equal and opposite at equal and opposite speeds like this. Does everybody understand from my hands? Yes? Okay. Now one of those plates is behind the screen. That you can't see because it's behind the screen, and the other one is in front. So one of them's doing this, and the other one from the back is doing that. Okay, everybody see that pretty much? And you're seeing in between the energy, kinetic energy, turbulent kinetic energy in between, and you will notice that it forms these stripes, that's hence patterns, and they're very regular. They have a wavelength and they have an angle. But recall that the plates are moving like this or this. So this angle here is just coming out of thin air. You see the remains of this streamwise direction, that's what it's called, in these things here. These are called streaks, these thin things. And you can situate yourself in the direction that is perpendicular to the one that you can see by noting that the distance between these two streaks is approximately the distance between the plates. So you see that the horizontal directions are much larger than the direction between the plates, which is this. Does everybody understand? Please ask me if you don't, or even if you do. Okay. All right, so you see that each of these stripes, these bands, contains many of these streaks, and we'll talk about them shortly. Okay, this problem, yes. Okay, so here are these are the prototype wall-bounded shear flows, plane Couette flow. Now you see a different view. Here now, you do see the distance between the plates, and their plates are doing this. So this is 90 degrees from the view that you just saw. And then there's pipe flow, where you have a pressure gradient that pushes the fluid. Poiseuille flow has the same geometry as the Couette flow. It has two infinite parallel plates, but now it's the pressure gradient, as for pipe flow, that is pushing the fluid, unlike plane Couette flow, where the fluid is put into motion by the shear with the plates. The plates are moving, and therefore that makes the fluid move. And all of these flows, as simple as they are, have this big puzzle, which is to say they undergo transition to turbulence, and which is not explained by a linear instability. Couette flow is linearly stable, this one here, forever, for all Reynolds numbers. Same with pipe flow. Poiseuille flow is linearly stable until Reynolds number of about 5,000, but the transition to turbulence is much lower, and it has nothing to do with the linear instability. And these are the approximate Reynolds numbers at which one sees transition to turbulence in plane Couette, pipe flow, and plane Poiseuille flow. So there's something going on that is not explained by linear stability theory. Okay, these are classic pictures. This is an obviously old problem. This is as old as you can get. I mean, this is flow of water or air or oil or something. And Mike and Predrag, you've heard this probably many times, and you can feel free how should I say, if I don't see you behind your screens, that'll be fine. You can go off and then come back if you want, or just turn, or sometimes what I do, I'll confess, I sometimes have the sound on, but I'm doing other things with the computer, and then I can come back when it's something new, and I won't mind if you do that at all. Anyway, Reynolds in the 1880s, that's the same Reynolds after whom the Reynolds number was named. He was the first to do systematic, what we call nowadays scientific investigation. He put dye in the center of a pipe, and you see that when it's laminar, when the flow is slow enough, the pipe in the center, the ink just stays in the center. When it's high, it mixes up. That's what you see with this ink here. It's mixing, and over here it's mixing in part of it. And that was in the 1880s. Then we see the classic approaches, or Sommerfeld, Squires. Those of you who have learned fluid mechanics have definitely learned those things. In the 1980s, that's when I view history as starting there, since that's when I was going to graduate school. And there were names like Orsag and Patera, Kells and Bailey, and they said maybe it's a 3D instability of a 2D flow. Then I went to Swinnyland, where I met Mike Schatz, and there they were saying that it was a chaotic attractor. You may have seen these pictures, and either in history books or in Predrag's course or something, a chaotic attractor. That was all the rage. Then the next fad or phase or fashion, we could say, or theory, was transient growth. And that was in vogue in the 1990s, where even if all the eigenvalues are negative, you can, if they are sufficiently non-parallel, you can have transient growth. And I guess the idea is that it would push you over into turbulent behavior. The thread that I'm following started, we could say, in the 1990s with Walev, who found that there was that you could maintain the smallest box in which you could maintain turbulence, called now the minimal flow unit. And this box is 2. Now 2, that is that small direction I was talking about, the one between the plates. 2 is by definition, one non-dimensionalizes plane current flow by half the distance between the pipes. So 2 by 4 by 6, and you could, that was the smallest box in which he could maintain turbulence. And then so he made he derived something called, that's now called, what he called, the self-sustaining process, SSP, and we still believe in that as being kind of behind the scenes in turbulence. What you have is a three element process where you have rolls that are like Taylor-Couette rolls, and they're shown here like this, rolls. This is between the plates here, rolls, and the rolls carry the fluid that is on the bottom up to the top, and the fluid that's on the top down to the bottom. It's clear if you think of convection, you know that rolls, convection rolls, bring hot fluid up and cold fluid down. And then after that, you have the streaks. Anyway, I won't go into that too much. The next phase in this historical evolution was the idea that turbulence was a chaotic attractor whose skeleton is formed by unstable solutions being of the type equilibria, periodic orbits, and unstable solutions in the context of wall-bounded shear flows, not content to use already existing nomenclature. They gave it a new name just to confuse things. They called it exact coherent structures, and I believe this name comes from Walev. And this idea, Predrag, you'll correct me if I'm wrong, comes from Svetanovich and Eckhart and Kawahara and Kida around 1989 and 2001. And it's been practiced a lot. Practitioners, by that I mean people who found equilibria and periodic orbits, unstable solutions, experimentally and numerically, and then tried to track turbulence by interpreting it in this way. And I will show you some pictures of that. This is from Predrag's Chaos book, and it's a movie made by John Gibson. And this is the fluid flow, and we're representing it in phase space. That is to say, we're projecting this large data set where there's, I don't know, let's say 100,000 or 1 million points in space of 3 velocity components, this or that. We're projecting it down to 3-dimensional space here, and we are going to track the evolution of each of these flow fields, which is a little three-dimensional object. And I don't mean three-dimensional in the sense of you have an X and a Y and a Z dimension. I'm talking about 3 scalars. And so here you see the fluid flow and its projection here. Let me bring that back. And so let me go back to that. So one sees there, this is the dotted thing is an unstable periodic orbit, and you see the purple thing is an unstable periodic orbit, and the dotted thing is the turbulent path. Is that right? I think maybe, yeah. Anyway, you see how it shadows it. It seems to be interested in what even though it itself is doing turbulent stuff, it seems to be interested in what the periodic orbit is doing. And another Georgia Tech is the big place for this. This is the work of Mike Schatz and his group, Roman Grigoriev and Jeff Tithoff and Balachandra Suri. Same kind of thing. Here, this is again phase, three-dimensional phase space where you represent each fluid flow by a point in this phase space. And so here is one flow, and here is another flow, but of the same. Okay, now let me tell you what that is. This is what's called Kolmogorov flow. You have magnets that are arranging that there's a force to the left and then to the right and then to the left and to the right. And when I say and then, I mean in this y direction and not in time. So you have a bunch of stripes of forces, and that so that makes shear in between each of these left and right arrows. And then you end up with solutions that look like this when viewed from this perspective here. That is to say, there's thickness, but it's very small compared to the rest. And here's one of these numerical solutions called exact coherent structure. And here's an experimental picture. And that's, so this is an experimental version of what we saw on the previous page. However, I'm not going to tell you about anything like that. I'm going to tell you about very large scale turbulence. And I'll tell you how large in just a moment. This is a picture from experiments done near Paris in France in around 2000 or to 2002. And this was due to a experimental breakthrough, and Mike, you'll correct me if I'm wrong, by Tillmark and Alfredson. And they realized that you don't need to move the plates, that you can just move a film that's on an infinite belt that is parallel to the plates. And that's much easier than moving plates in an experiment and keeping them exactly parallel and exactly separated by this distance. You can have your plates and they are separated by this distance and they are parallel, but you don't have to move them because the only thing that's moving is a film here on this infinite belt. Okay, so that allowed for the first time there to be experiments in large aspect ratio, a plane couette flow, and this was taken advantage of by Prigent and Douchot, and they did a very large plane couette experiment. You see how large it is. I told you already that the standard for non-dimensionalization is the half gap, and I remind you that the gap is what you don't see here. It's perpendicular to this picture. You're seeing approximately the midplane, or else maybe from above. Okay, so the gap is in between, and yet here you have a length that's 770 half gaps, and this is something like 350. So you see everything is much larger than the gap. Okay, and also, okay, this will come up in a little while. The Reynolds number for plane couette flow is basically the difference between the top and bottom velocity and the difference and the height of the between the gaps, between the plates, divided by 4 nu, and this will take on some importance later. So these Reynolds numbers are in the vicinity of 300 to 400, quite low, and easily resolvable numerically. Now, let me tell you, I told you I wasn't telling you about that other stuff. The other stuff, this is the Gibbs, this is the MFU, the minimal flow unit of WLF, the 2x4x6, and the videos you were seeing of plane couette flow were boxes that were maybe this size or maybe 10 times this size, and the Kolmogorov flow of Mike Schatz was also about maybe 10, 20 times this size, some 10 times this size, maybe. But the bands are much bigger on a much larger scale. Again, you see the angle, and again you see that you see these structures that do remember that the streamwise direction, and you see how big the bands are relative to the gap, which is like this. Questions? Okay. So this is very important. That's why nobody saw them before, because nobody did very big plane couette experiments. However, what had been done before was they had been seen in Taylor couette flow in the 60s by Coles and Van Atta. And here's an old picture, but then this is this is the visualization by Andrek et al. In Texas, but of what Coles and Van Atta had seen. This is Taylor couette flow, that is to say, the plane couette flow is the flow between differentially translating plates. Taylor-Couette flow is the flow between differentially rotating cylinders there. And here is a view from the top of the outer and inner cylinders that are counter-rotating. And here's a piece of turbulence, as you saw in this picture here. There's turbulence, and then there's laminar, and then there's turbulence, and then there's laminar. Okay, so you see that. But here you could think, as Coles and Van Atta and Andrek et al., that you have a patch of turbulence and a patch of laminar, and it's amazing that they coexist, but that's about where it stops. Prigent and Douchot, by doing these very large aspect ratio experiments, they saw that this patch of turbulence was actually one of a repeating, a pattern, a regular pattern of bands with a regular wavelength and a regular angle. This is Taylor-Couette flow, but seen with mirrors from the back, and you see, so you see the whole thing, and you see how regular these patterns are. And if I, you don't see your own faces, do you? Right? I mean, if I do this, you see my cursor, yes?
Yeah.
Okay, you don't see, okay. Anyway, this is the aspect ratio they used. So compare this circle with this one. You see that here, the gap, the circumference is maybe what, 6 times the gap? But here, the circumference is many times the gap, which is, this is realistic, which is about this, like this. And this is quantified by the radius ratio between them. Here, the radius ratio is 0.983, and here it was 0.88. So this is why Prigent and Douchot could see these patterns, both in the Taylor-Couette flow and in the plane Couette flow. Are there questions? No? Okay. Okay, then this was simulated numerically in 2009 by, okay, I say we're the first to have simulated them, but I'm showing other people's simulations first. Or in fact, I could go back here. And this is our simulation. What you saw, the first slide was a color version of this. This is our simulation just overlaid on the experimental picture. And you see here this characteristic wavelength of 40 half gaps and the angle of 24. So these are some other simulations of Taylor-Couette flow and of plane Couette flow. Duguay, Schlatter, and Henningsen, and here Messiger and Melabowski, Avila Marquez. Okay, and now this is a movie, and in the movie you're going to see. Okay, we start off at Reynolds number 500, where we have turbulence. And you recall I told you that turbulence is in these flows takes the form of these streaks. So this is this blue, red, blue, red. These are the streaks. So this gives you an idea of the depth that you don't see. And why do we see blue and red? Because this is color coding for fluid going to the right and fluid going to the left. When we are laminar, all the fluid going to the right is on top at the top plate, and all the fluid going to the right is at the bottom plate, red. But when you have turbulence, you get these rolls, called things streamwise vortices, that mix it up. And this brings left going fluid up to the center, right going fluid down to the center. And so that's what you see. That's what you're seeing here in the mid plane. When you have turbulence, you see right and left going fluid arranged in streaks. And that's at Reynolds number 500. And now we're going to lower the Reynolds number. And we still see these streaks. They have to be wavy. That's part of Woleff's thing. And you see that they're waving about, and we're lowering the Reynolds number to 350, and you will soon see, of course, they're less vigorous, the Reynolds number is less, but in addition, you see these laminar places appearing, that's green, where the fluid is not moving, it's halfway, as it should if it's halfway between the front and the back, but you also see the angle forming, and this is just Navier-Stokes being simulated, and this angle forms spontaneously. You see this angle. This angle is about 24 degrees. There's nothing wholly about 24 degrees. It's a range between, say, 22 and 40 degrees. But it depends on Reynolds number. That's one of the things that Douchot. So you see the spontaneous formation of these bands. And that is all that I'm talking about. I'm not talking about what makes turbulence exist. I'm talking about these bands and only these bands. Questions? Nope, still not. You sure?
Yes.
Okay. Okay, so here we go. That's that same picture again. Okay, so Dwight Barclay's idea was to simulate it not in a nice rectangular container where the streamwise direction was X and the spanwise direction was Y, but in a direction, in a box that was oblique, where it was perpendicular to the bands. The bands are in this direction, and this is our long direction. And that was very clever because it allows you to save a lot of space. Statistically, along this direction, it's all the same. This is turbulent. It can't really be, and you can't reduce this dimension to nothing. You've got to have room for the turbulence, but it's only in this direction that you need the room for these very widely separated bands. So that allowed for these kinds of simulations to be done economically. So here is such a simulation. This is that long direction, and here is Reynolds number being gradually lowered, and you see that the laminar section that appears spontaneously, just as you saw in the movie. And here's a long series like that. Again, this is a sample along a line that is perpendicular to the bands. And as you see here, the Reynolds number is lowered gradually, and but in steps, and you see the bands forming, and you see wavelength. And so the questions we would ask are, what selects the wavelength? What is the upper threshold? How do we define it, and how do we evaluate it? The bands disappear here. That's the lower threshold. How do we define that? Since it's all kind of statistical. And what is its Reynolds number value? And what are the mechanisms that keep the turbulent laminar pattern maintained? You'll notice here that you went, maybe you don't quite see it, you went from 3 bands, so a wavelength of 40 to a wavelength of 60 here. I mean, that's to say you have one here and here, but it's periodic, so this is just part of this. When this band disappeared, you had 3, and now you have 2. So something told it to do that. And here, this one disappears. There's only one here because it's periodic, and something told it to do that, and then eventually it disappears. So what made it do that? And here again, 2 samples, the one that you just saw, and here's a longer one, which did a funny thing, which shows how much the fluid wants to do this. When one band was supposed to disappear, as it happened here, at 310 it was, instead, 2 bands disappeared. They didn't confer with each other. They didn't collaborate, and they both disappeared. And now the pattern's unhappy. It does not want to have a wavelength of 120 at 320. No, it wants to have a wavelength of 60. So it keeps trying to make a new band, but it doesn't make it until finally it does. This shows you how much it wants to have a wavelength of 60 here. That's really a feature of it. And so finally it succeeds in making another band, and it goes on there. Okay, now I'm going to tell you about the mean flow that accompanies this turbulent stuff. I haven't told you anything about it so far. Here, let me go here. Right. This is, again, a streamwise, spanwise view, and these turbulent bands are accompanied by a mean flow that is along the bands. This is a sort of top view, 3/4 of the way up, and you see that on this side of the band, you're going in this direction, and this is the bottom, and along that part of the band, you're going in that direction. And this is from Duguay and Schlatter, so people know about this mean flow. And this turns out to be a very important element. We'll go back here. Oh, oops, no, and that's not what I meant to do. Come on, come back. Yes, okay, so this is a data set which is pretty stationary. That is to say, it's statistically stationary. And we are going to average in time and also in that short direction, which you don't see here. The short direction, when we do that, we find we have gotten from a 4-dimensional data set, X, Y, Z, T, to a 2-dimensional data set, Z, where you have turbulence, laminar, and Y, the distance between the plates. So here you are with this data set between the plates and Z, and we have subtracted the plane Couette flow. This is all a deviation from it, and you see clearly here there is flow. Okay, I'm sorry. The turbulence is here. This is a turbulent patch, and here is another turbulent patch. And you see here clearly this is flow into and out of this view. So this is along the band. The band is here. This is the turbulent part. And at the top, you have flow going one direction, say into the board. And here at the bottom left, you have flow going out, going the other way. Okay, everybody understand this mean flow? This is a perspective view of a different perspective of what you see here. right? This view is streamwise, spanwise, and this one is Z, meaning as you go along the from one band to the next, and this is between the plates.
Are you only just averaging one band wavelength there, or you're just showing only one band wavelength?
No, averaging only one. This is a length of 40, and
Okay.
this is the whole thing. The whole data set is here.
I see. Okay.
You get very clean data from.
All right, thanks.
Okay, so we found some amazing things right from the beginning. That is to say, you can see how regular this mean flow is. And indeed, if you try to decompose it in Z trig functions, you find you only need one wavelength. Right? You have constant and then cosine and sine, and that really takes care of everything. The mean flow. And now, okay, so that was amazing, but you'll see more about that later, perhaps. Now, this is much more recent work by our PhD student, Sebastian Gumi, and he had the idea of suppressing the large-scale flow. He's going to do that, you know, the way you can do it numerically. He just said no to these low, the large-scale flow, which is blue here. This is Fourier modes, and the low K is big wavelength, and so he just suppressed that. I mean, you can't just suppress large-scale flow. You need it for the hydrodynamics, but you can suppress it the span-wise large-scale flow and still keep your thing going. So here, the red is the, I'm sorry, hold on. The blue is the natural spectrum, and then the red is the suppressed one, where he successfully suppressed it. This is the energy of the little scales, the streaks over here. So they're still there, and they have to be, or you couldn't have turbulence. You could imagine that the streaks and rolls are the texture of turbulence. You need them. So they're still here, but that low K stuff is not there. And here is plain Couette flow with its not quite, if we'd run it for longer, it would be more regular with its bands, but you see the basic features. That's to see, you see the flow along the bands, and you see the turbulence, which is here. This is streamwise velocity here, or no, yes, it's streamwise velocity in a tiny, tiny bit here. Okay, everybody see this? But now when you run it by suppressing it, you see this. This is what it looks like. So you still have turbulence. You still have turbulence. And let me tell you more about it, because it's not so clear from these pictures.
Can I ask you, how does it do the suppression? Is done just by filtering the spectrum at any time?
Yes, constantly takes out the low K spanwise modes.
Okay.
And so here now, okay, what is this? This is in time, and this is in Z, that direction that we were talking about, that where you see the alternates between laminar and turbulence. And in plain Couette flow, if you start at 320, you get one band here. Remember that we had just one band back in those pictures here. This is, again, there's blue and red because it's the, this has to do with the, anyway, this is one band. 325, it's spreading, and you see sometimes bands dying, right? And then you see them dying, and you see them splitting. We'll come back to that later. And at 380, well, the pattern just grows into regular bands. This is all in the, this direction is perpendicular to the bands, so they're not, anyway, they're perfectly fine. If you suppress it, you see those same things. The Reynolds numbers are slightly different, but you see for low Reynolds number, the turbulence dies, it continues and spreads a little, and 450, it fills a triangle. But here, it's like pixels. It's pixels of sand. You no longer have the bands, you just have pixels. So it's not that it's suppressed turbulence, it's just suppressed the bands. The turbulence is fine. It's just not forming into bands. Everybody understand that? Okay, so this was very new, interesting. So here,
no streaks at the scale of the.
No, there have to be streaks. There are streaks.
Yeah. Okay.
Oh, I'm sorry, we're missing there's another picture taken here that looks just like this.
Okay.
There have to be streaks, so there could be no turbulence.
Yeah.
There's low streak. Okay, I should replace this by the one that has this too. In a picture, in a thing that big, it's also got that. But this scale is so much bigger that you don't see the streaks. Yes, it has streaks. And again, these are comparisons of with natural and with that flow suppressed, the large scale spanwise flow suppressed. So you see it doing its turbulent thing, but there's grains of sand instead of bands. And you can turn off this patterning. Okay, so was aspect number one, mean flow. Aspect number two, Poiseuille flow, is Couette flow plus upside down Couette flow. Okay, so let me tell you more about that. Bands appear also in Poiseuille flow. Here are visualizations of Poiseuille flow where you also see these turbulent bands. The first were carried out by Tuckerman in Japan in 2004-2005. Now you see again the same kind of series. This is the direction perpendicular to the bands. You see us lowering the Reynolds number and you see the bands appearing, but now you see that they are not traveling straight up and down. They are, they're not going, they're moving. They're moving relative. All this is, of course they're moving. The Poiseuille flow is of course moving, but that's not so. This is relative to the bulk velocity. We're in a frame where the mean flow is 0, and yet the bands are moving with respect to that frame. Sometimes they're moving slower and sometimes they're moving faster. And that is very regular and depends on the Reynolds number, just like the wavelength and angle as we saw before. More specifically, if you do the speed, again, this is the band minus the bulk flow as a function of Reynolds number, you see the Reynolds number, regular Reynolds number dependence of that speed. You also see something else. This is done with different lengths. I mean, we are being periodic in this direction, but perhaps the bands are affecting one another and affecting, right? And because this is not, when you're periodic, you might be affecting the other ones. And we see here, though, that once we get to a domain of size 100, we are big enough, the velocities stop evolving. That's the intrinsic velocity of a band. Whereas when we had lengths that were 25, 40, and 50, they were not banging into each other, but affecting one another, repelling or attracting each other. So we didn't get the same.
Laurette, can I ask you something? At what horizontal level you are plotting this space-time diagram? Are you in the boundary layer or near the center?
Neither. It's something like 3/4 of the way up. 3/4.
3/4 from the boundary layer. And
No, there's no such thing as a boundary layer here, or the whole thing is boundary layer. We're much too low to have real boundary layers. This is, I'm sorry, let me take my coordinates, I'm sorry, from -1 to 1. Okay?
Yeah.
And this is at approximately 3/4.
Okay.
So it's not 0, it's not 0.9, it's not 0.8, it's not 1, it's 0.7 approximately.
Because here I see wave dispersion. I see the same things in my work, the one that I send you. Here, there is a water wave dispersion.
Yes,
Long waves travel faster than shorter waves, which is very clear in your diagram. And I see the same things in my work. So
interesting.
Because I did the channel flow, which is similar.
Yes, the channel flow, it's the same. This is plain Poiseuille flow and channel flow are two names for the same thing.
So at 3/4 there, we are near the boundary layer. So we also find they are basically water waves. So they are the same dispersion as water waves.
Yeah. I will ask you also to see, thank you very much. I will ask you to see also these Reynolds numbers. We're no longer in the 300, 400 range. We're in 800 and 1900. And we're also seeing wavelengths that are 20 and not 40. Why are they different? Well, that turns out to be trivial. It just has to do with the definition of the Reynolds number and of the length scales. In plain Poiseuille flow, you have, you take your half gap to be the length, but that is the full length of a shear layer here. And hence there's a factor of 2 there. And you take the maximum velocity to be the velocity scale, whereas in plain Couette flow, you're taking half the velocity difference, that is to say, between this and this to be the velocity scale. So you automatically have a factor of 4 between the two definitions of the Reynolds number. And the right way to think of plain Poiseuille flow is 2 shear layers of opposite signs, this way, the 2 Couette flows. Now I will confirm that to you in just a moment. One very vague confirmation is these Reynolds numbers, the 300 of the transition between turbulent in Croquet, Poiseuille 1,000. That's not a factor of 4, but after all, it's not exactly twice it. And pipe, there's again a trivial reason why the transition is for 2,000 for pipe and for 1,000 for Poiseuille. It's because for Poiseuille you use delta y as the length scale, and in the Reynolds number, whereas for pipe you use the diameter. So there's your factor of 2. Okay, so let me show you some things. This is the same things you were seeing before. What do I mean by before? I mean here I showed you the mean flow that goes along the bands on the top of one, along the top of one, and along the bottom of the other. Right? The mean flow. It's the same one, excuse me, it's like this and this. Okay? The mean flow, here I'm showing you the same thing, but this time I'm showing it to you stretched. This is not a correct aspect ratio. Okay? So here you see the flow along the turbulence is here. You see the flow along the top and along the bottom in opposite directions. And what does that look like in Poiseuille flow? Well, it looks like this. And if we put a couette and a reflected couette, you see that we get the Poiseuille. Now, not exactly, because a couette flow, of course, you have to go to 0 at the plate. So let's do that. Here we have 0 at the plate, but let us take away that 0 at the plate, move it forward, move them together, and there you are with Poiseuille equals couette plus couette. Another way to see that is with the forces, but I'm not going to tell you about that because I'm running out of time and I want to get to other things. But I hope you will take my word for it now that Poiseuille is 2 couettes and everything is just the same. This is the forces. Now I'm going to take off the walls and make Walef flow. And so here's Prandtl saying, what? No walls? And this is, Bookman, no walls. No walls in wall-bounded shear flow? Now that doesn't seem right, does it? Well, the key word is not wall-bounded, but just bounded. Here is Walef flow, toy model of plane couette flow. The wall, you have free slip boundary conditions instead of rigid. That is to say, you cannot penetrate, you cannot go from one to the other, but you can slip along. So what is transmitting your velocity? Before it was transmitted by dragging, by viscous drag along the plates. Well, now you have to have a body force, and this body force is deliberately made to be sinusoidal. So here it is. Here's the flow, which is responding to the sinusoidal forcing. It is half of a sinusoid. Okay. And this is what was used by Walef to prove his thing. He did it this way without boundaries. It was used for the self-sustaining process. And this is, say, confined Kolmogorov flow. If you'd done this over and over, you'd continued the sign here and then up higher and higher and higher, then you would have Kolmogorov flow. You agree with me, Mike? Right? This is just one piece of Kolmogorov flow, half a wavelength of Kolmogorov flow, right?
Yes,
okay.
I was muted, yes.
Yes, okay, good, he says yes. Okay, so no boundaries, no walls and no boundary layer, because there's no. Okay, other people, this is Walef, who studied Walef flow, obviously it's named after him, and other people. And let me show you then more about Walef flow. This is the laminar flow. Recall that it's sinusoidal in the case of Walef flow, and straight, we know, for the case of plane couette flow, straight profile, laminar. Now, when we go to the mean flow, when we have turbulence, we're familiar with the fact that plane couette flow, you have this S-shaped profile, that the flow likes to have kind of the same velocity in the center, and all the difference is taken up by the boundaries, by the boundary layers, this stuff here. But in Walef flow, since it doesn't feel the wall so strongly, it has a pretty much straight turbulent mean profile. So that's funny. And let us do a little more. What we want to do is study plane couette flow, that red thing, without walls. We just want the interior of it. We don't want to be perturbed by the walls. Once we've decided that walls are not the important thing, that the important thing is shear, and we only wanted the walls to give us the shear, then we try to forget about this. So we're going to make a Laurette flow of whose dimensions are like this. We're going to use we're going to change the dimension. That's just a post-processing. We're going to consider that our plane Couette flow is not the same. Anyway, you see what I mean. I'm just doing Laurette flow, and I'm doing that with the goal of simulating the interior of plane Couette flow. But I'm doing Laurette flow, and I'm going to compare. Okay, so here we go. First of all, it makes bands. Look at this. This is Laurette flow, and this is plane Couette flow. And this is the same Reynolds number, and look how similar they look. They don't look exactly as the same. You see that there's less small structures here, but they are very similar. And when I say 350, that is because we corrected the Reynolds number by this factor to allow for for this change. That is to say, where our scale is not to be taken like this; it's to be taken anyway. You get it. We've corrected it this way to get a Reynolds number that is a proper comparison, and we see it's the same, and that's amazing. So you do not need walls to make the bands. Then, okay.
5 minutes left, Laurette.
Okay. Okay. So let's see. Here we have this is you've seen this before. What we mean, this is plane Couette flow, the flow along the bands. Here you have, I'm going to draw that limit there, that size here, and I'm going to cut here. And what do I get? I get Laurette flow. So it's really as if I have cut off the boundary layers. So you see, you don't need boundary layers. You don't need boundary layers. And so that is nice theoretically, because boundary layers are actually not playing a role in this phenomenon. And that's nice theoretically, but it's also numerically, because we know we need a lot of resolution for the boundary layers. There's rapid change. Then we model the Laurette flow by taking fewer, and that works out too. Okay, now let me see what of my stories I would like to tell you. Yeah, okay, I'm going to tell you, we want to find out the lower bound of the lower bound of when there is turbulence. So here, okay, what is this? Oh, I should show you first. Here we're pixelating laminar versus turbulent, and we have a huge, huge domain, very, very huge. In fact, I think I need to go back a tiny bit. I have here a domain that is, where is it? You saw this picture, that's this big. This is the minimal flow unit. This is a band unit, and this is what we're simulating. All of these are bands. They're very little, and our system is of size 2560 by 2560, far larger than any system that was ever simulated before. And this is what you see. You see that as you see that the bands remain. You don't see pixels, you see bands, and they have that angle. Even in this huge domain, when they're very irregular, you see bands at an angle, and you don't see going down to a little pixel. There are pixels sometimes, but they're just bands, and that is the basic element of turbulence in the wall-bounded shear flows, and that's true even without the walls. Okay, so by this means, we were able. The question was, is it continuous or discontinuous, the transition? And if we measure the turbulent fraction, it had been thought that it was discontinuous. Hold on. That is to say, both experimentally and numerically, these people had measured the fraction of the experiment that was turbulent, and they saw it go down suddenly here at 324, and at the same thing experimentally. So you'd think you were right. But why did they see that? You can see why you need a huge domain. If your domain was smaller, you would think this was laminar. It's because the basic element is one of these bands. And what's more, the transition does not happen by the turbulence becoming weaker. Each of these bands is pretty much as strong as it would be at a higher Reynolds number. It is just that there are fewer of them, and they are sparse. The transition is not from weak flow to strong flow. It is from sparse flow to full flow. And that is why we needed to do this huge experiment. Even when we had our turbulent, our large domain, we too have a gap It's discontinuous because there's the last band that you can see. We can't do an infinite domain. When we did this, the turbulent fraction as a function of Reynolds number, we also saw that it followed a power law that was not the square root that I'm so used to seeing from bifurcation theory, but physicists apparently have a different exponent, 0.58, that comes from the theory of directed percolation, which I knew nothing about, but this is a case of directed percolation, and directed percolation is exactly like this. That is to say, you have or you don't have, and that follows things like forest fires, you're on fire or you're not, or epidemics, you're sick or you're not, and it disappears by becoming not weaker, but by becoming sparser. Your fire in a small, when the fire is starting, it only occupies a little space, and when you get more fire, it takes up more space. And similarly, one person with COVID out of 1,000 is not less sick, he's just one person, and when the COVID spreads, everybody has it. Hence, it's that kind of transition, and that's what we saw. And I think I'm going to end here because it's time to end the seminar. Am I right? Right.
Yes,
my last,
yes.
but I won't tell it. Okay.
Thank you very much, Laurette. Thank you. So, any questions, our speaker? Matt?
Yeah, I was just gonna ask if you, so these are all for square periodic domains in the non-wall normal directions?
I'm sorry, all. I showed you two different kinds of domains. I showed you a very large domain like this, which is oriented streamwise, spanwise, and I showed you narrow domains that resembled, well, this is not ours, but something like this. What are you talking about?
I think I'm talking about the large domain. So it's periodic. I was just curious. Initially, I was confused on if the two length scales and the periodic directions were the same, and if that had anything to do with the emergent angle. But this convinced me that that's not the case. So it's this image here.
Okay. Oh, I'm sorry. I do want to say one more thing, which is not the my seminar, but hold on. Oh yeah, I had a lot more to say, but that's fine. I want to make an advertisement for a theory that that should be published sometime for plane co-ed flow, a minimal model by Santiago Benavides and Dwight Barkley, and they're working on publishing it, which shows the same kind of behavior, bands and all the rest there. Okay.
So, Laurette, this transition, the pattern that you show from the transition to they look like Ising model patterns. Like, I wonder if there is you can use the Ising model to, because even there, in the Ising model, there is a critical temperature below which the flow starts to acquire coherent structures. I wonder if, they look exact. I don't say exactly, but when you were showing them in the videos, the video that the
video, yeah. Okay.
They remind me of you got this video, the other one, the black one.
Yes, this one, yeah.
Yeah, it reminds me of the Ising model patterns.
Yeah, but I guess Ising model doesn't have a definitive angle, right?
Yeah, of course. This is more, but already, maybe there is because this is all, because to reach these patterns, you get to steady state in your simulations, is right?
Well, it depends on your Reynolds number.
It depends on your Reynolds number.
But yes, at the critical one, you don't. You just keep going down. But otherwise, yes, you go. Just a second. Let me hold on. Let's see if I do. Yes, you do.
You see, look at this. It's so there maybe this turbulent energy is basically the Hamiltonian, so the energy of the Boltzmann model.
Okay, but let me tell you something important that I don't know enough about statistical physics to tell you, but this is one way. That is to say, any particular site can go from turbulent to laminar, but it cannot go from laminar to turbulent. It can only be infected by its neighbors. From my understanding of Turing, it's symmetric in the two directions, right? You can go from -1, Ising, go from -1 to +1.
Yeah, of course.
It's very important that there's asymmetry for this
yeah.
directed percolation, that you can go from turbulent to laminar, but never from laminar to turbulent, except being infected by your neighbors.
Well, you can tweak the energy of the icing to introduce asymmetry. That can be done. So is Pedrak, Mike, any questions even on this icing model? What do you think on this part?
Yeah, so I have a question about things like the pattern wavelength.
Yes.
So what's the latest on understanding that? Yeah.
Well, okay, Dwight thinks he is getting, I think not the wavelength, but the angle, but I think once
Okay.
he'll also have a wavelength. But, and he thinks he understands it. His latest word, as of, I think, 2 days ago, was he thinks he understands it mathematically when he manipulates his model and does things with signs and this and that, but he still feels he does not understand it physically. He thinks,
so there's no stability. Is there like a stability theory of something on the model
there is
indeed.
There is indeed. But that's not an explanation. That's just another kind of calculation.
Yeah.
That's
okay.
He thinks that he thinks that by manipulating these. Okay, let me tell you just a tiny bit more about these equations. The point here is that there's Q, which is turbulence, a Q field, and it has a law that is, you know, done with various hypotheses from Pope and blah blah blah. So that makes it different from actually doing Navier-Stokes. And he thinks he can do this with very few variables, and that all he needs, all the hypotheses that are in here are hardly even necessary, and that he just does it from the Navier-Stokes part and the angles and, you know, advection and kinematics. But he says he doesn't understand. Yeah, so he has done a linear stability analysis, which he believes does that, but that is, he doesn't feel it's an explanation, right? I mean, you know, it's more of an explanation than not, but I mean, we feel when we get our wavelengths in, I feel, how would you know you had an explanation? Well, if you do Rayleigh-Bernard convection, we know we have this feeling that rolls want to be round, right? That's the shape they want. And sometimes they're not round because we have plates, and so there's a boundary layer, so they're kind of elliptical, but basically they like to be round. Wouldn't you say that, Mike?
Yes, aspect ratio one-ish.
We'll
yes.
say something like, well, because that's the best way to transfer heat, and they lose the least in this. You know, we have words for this, right?
Yeah.
And he doesn't yet have words for the angle or the wavelength. He has calculations, but not words for it. So, you know, we do the same with Kelvin-Helmholtz, right? We would say, oh, that's the scale of the, you know, once you have words for it, and you can then you feel you have some understanding. But when you only have equations, I mean, he has simpler equations, but they're still just equations.
Right, got it. Another question that's back on the Poisson flow and the sort of traveling bands. Is there a sense of like convective versus absolute instability associated with those?
Good question. One of my lifelong, I mean, I guess I can say by now, lifelong regrets is that I have never mastered convective versus absolute instability. That I need to learn that, perhaps, and also need to learn about absolute versus discrete and continuous spectrum. And I want to learn Lie group representations. And when I'm finished with all three of those, then
you'll explain it to us.
So I don't know.
Regarding this flight, what is the physical origin of this wave dispersion in turbulence? You know, because usually, you know, when we talk about wave dispersion, they only think about ocean waves. But apparently, you know, turbulence, you know, it seems as some hidden wave dispersion, you know, that which, I mean, if you talk to hardcore turbulent guys, no, they don't believe it. So, but so, I mean, what could be the physical, what could be the physical, I don't know.
I'm sorry, I think I just want to go back to Mike and give now my ignorant answer, which is no. And the reason I say no without any understanding is because really, it's exactly the same in plane Poisson flow as it is in plane Couette flow, where there is no such notion, where they just stand still, right? Don't you agree? The wavelengths are the same. I mean, if you measure them right. The forces, you know, everything is the same. The forces are balanced.
The thing I'm a little confused by, though, is this. I mean, in plane Couette flow, there is a zero mean flow, right? Whereas you have this, a non-zero.
Yeah, that's by symmetry necessarily. Plane Couette flow is centrosymmetric,
Yes.
Things can't go right, whereas here they can. Quasi
Yes.
flow has, there's no symmetry between upstream and downstream. So
Right.
yes,
So that, in my physical way of thinking, you have like mean flow, right? And then that admits the possibility that these, you can have structures that advect relative to the mean flow, right? This notion of it as convective versus absolute instability. It seemed, I don't know, that's.
well, okay, absolute and convective, and I don't, so I really shouldn't say anything more about it.
Okay.
I have to apologize, but there is pizza that is waiting for us. So
We have
Can I
another
have
question online
have
here.
some? Can I have some? Can I have some? Can I have some pizza?
and the next
No.
time we're here, we're gonna bring
I
you
want pizza. I want pizza.
the best in Atlanta. So and we have also there is a class coming here. That's
But you have
Okay.
one question online with someone who's very patiently waiting. I think you want to field that.
Jorge, do you have a question?
Yeah, there's no time. It's okay. I just wanted to comment that I'm from the traffic flow theory research area, and
Oh.
some of the pictures are really reminiscent of congestion in cities. So especially the one at large scales that you have. So if we could flash it for a second, the large scale experiment. So
This
right,
one?
so those clusters that you see are very similar to some of the traffic flow models. And you see really two angles, right? Like +1 or -1, I would say.
Yes.
It's right. So my question is, how does that compare to the 24-degree angle you mentioned before?
Okay, I think that this is not +1 -1. I think this is 24 and -24.
Oh, okay.
I should have a protractor that I could put here on the, but I think if I do this, maybe it's pretty clear that it's not 45 degrees. Don't you think it's flatter than 45 degrees? Don't you think this is flatter than 45 degrees?
So.
Yeah.
Right, but there's only two speeds, right? Plus or minus that. And that we see also in traffic, which is very very nice to see here. And also we see percolation, directed percolation, and many of the same things. So yeah, I'll keep an eye on your work. Thank you for the presentation.
Well, thank you.
So what about the wave dispersion? Do you have some intuition on that?
Me, none. I should say, the same as I said to Mike, I'm really not from the waves community. I do Faraday waves, but my background is really in elliptic problems in Terquet and Bernard, and I don't know much about wave phenomena. So I would need to learn about that. You're saying that, okay, but you're telling me that different wavelengths, I mean, I know what a dispersion relation is, and you're telling me the speed depends on the wavelength, yes?
That's what looks from your plots.
But I wouldn't, okay, but I don't think we can quite say that, because as the Reynolds number develops, you have a change in speed and in wavelength, and how you can't really.
I mean, for a given Reynolds number, different wavelength on your diagram on the left. If you fix it down, no, on the right, sorry, here. For a given Reynolds number, you see that the black points are short, small LZ.
Ah, you're going to, yes, we're going to force.
Actually, this is basically capillary waves. Shorter waves travel faster than longer waves, which that's what I found in my channel simulation. So
you're saying when we make it be periodic in a way that where it doesn't match the other ones, then it is traveling faster. Yes.
It would be nice, yeah, if you do the 3D.
You are right. Yes. Very interesting. Yes. Thank you. We were only using this to find out the speed when they're, the asymptotic value of the speed. We did not think that this was an experiment by itself to change the wavelength. Thank you very much.
You're welcome. So, I would be curious to see, if the origin of this dispersion.
Yeah. That's I only viewed it as an imperfection. I did not view it as a phenomenon. Thank you.
Actually, it's capillary. It's capillary dispersion. Shorter waves travel faster than longer waves. That's pretty cool.
Shorter waves.
I found exactly the same.
Yeah.
So
Yeah.
it's, okay, so, thank you very much, Laurette. We would like to stay here, but we need to.
Sure.
There is
Enjoy
a-
your piece. Thank you for giving me.
Excellent talk, Laurette. Good to see
Thank
you.
Wonderful.
Give my best to Dwight and your kids.
Okay.
We're not so